Okay, 2003, in an experiment, sorry, 2003B, question 3. In an experiment, a sample of an unknown pure gaseous hydrocarbon, again, hydrocarbon means just hydrogen and carbon, was analyzed. The results showed that there were 6 grams of carbon and 1.33 grams of hydrogen. What's the empirical formula? Remember, the empirical formula is the simplest whole number ratio. So we have 6 grams of carbon and 1.344 grams of hydrogen. And just remember that inside a formula, a chemical formula like H2O, that's a mole ratio. So the first thing we're going to do is we're going to convert both of these to moles. So there's 12.01 grams in a mole of carbon. And so this ends up being, and then this has 4 sig figs, and this has 4 sig figs, and you get something like 0.49995 or something, but to 3 sig figs, this is exactly half a mole of carbon. And you can kind of see that 6 is half of 12. And then, again, if it bugs you, you can put a 1 here. However, the molar mass of hydrogen is 1.008 grams in a mole. And so you end up with 1.333 moles of hydrogen. And now I teach this all kinds of different ways, but if you wanted to do the silly looking formula, you would get this. Um, and then again, remember, you have to have whole numbers, so then you divide through by the smallest number. And after you do that, you end up with C1H 2.667, keeping in mind that this is 2 2/3. Again, remember sometimes, so step 1, convert percentages to grams if necessary. It isn't because we got grams. Step 2, convert grams to moles. Step 3, divide through by the smallest number of moles. You can either do it up in the formula or you can do it here. I don't really care, but if you do this, this is exactly 1 mole. And then and again, why can you do this? Because you're changing the numbers, but you're not changing the relationship between the numbers. And then we're going to multiply by 3, and so this ends up being 3. And then if you multiply 2 2/3, which if you remember your 7th grade math, 2 times 3 is 6 plus 2. This is 8/3 times 3. This ends up being 8. And so the answer to this first part is C3H8. And that's a tougher one because you have to do the 4th step. If you divide through by the smallest number of moles and you still don't have all whole numbers, sometimes you have to do a 4th step. What's the molar mass of the hydrogen? This is one of my favorite formulas in all of chemistry. I'm going to quick derive it and then erase it, and then just use it. So remember that PV equals nRT. I call this the Perv-Nerd equation. This is the most important equation. Everything comes from this because it relates the pressure, volume, and temperature of gas to the number of moles of a gas. And moles is the most important concept in all of chemistry. But keep in mind, just go out and look at part 8. If you're given grams, how do you get moles? Well, you take the mass and you end up dividing by the molar mass. And so what happens is the number of moles can be calculated by taking the mass divided by the molar mass. And so now if we take cross products, I'll switch colors, but we get PV molar mass equals 1 times little m RT, RT, and then to get molar mass alone, you divide by PV. And so I end up with this equation that the molar mass of a gas is calculated taking Mr. T, the guy from the A team with the gold conquers over pervs. The other reason I like this formula is if they give you density from chapter 2, one of the first things you learn in here is density equals mass over volume. So you can take this equation and solve it like this. I generally don't. When I see a density like this, 1.96 grams per liter, I just put in, liter. I know there's an implied 1 here. I just put in the mass is 1.96 grams and the volume is 1 liter because that's what it means. But anyways, erasing all of that, however you do this problem, just know that the AP test loves the molar mass of a gas, um, because the formula is not on the formula sheet exactly like this. Um, and because of that, um, they just like to see if you can do it. So very quickly, I'm just going to pull this out. The molar mass of a gas is Mr. T conquers over pervs. What I'm going to put in for mass is 1.96 grams. What I'm going to put in for R, this is the value. They always do gas laws in atmospheres. Now, if you look, 0.0821 was what it will be on the scoring guidelines, but when they did the test revision back in 2003, 0.08206. They used to be on the formula sheet 0.0821, but for whatever reason they went to 4 sig figs. And then this is, sorry, I screwed up. I'm going to grab this stupid eraser. Back to the pen. This is liters times atmospheres over mole times K. And then it's 25 degrees Celsius, but we have to be in Kelvin. So 273 plus 25 is 298 K. And so then this is 298 K. And again, if it bugs you, there's nothing here. Put a 1. K cancels with K. P is downstairs, and so I'm going to multiply by the reciprocal just to get it downstairs. 1.09 atmospheres. Atmospheres cancels with atmospheres. And then I told you I would just do 1 liter, because that's what this means. If you had exactly 1 liter, the mass would be 1.96. And then liters cancels with liters, and then a really cool thing happens because you end up with grams on the top and moles on the bottom, which is cool because that's a unit for molar mass. And if you do that and you round to the appropriate number of sig figs, because this has 3 and this has 4, and this has 3 and this has 3, and this is an implied one, so it has infinite, you get 44.0 grams per mole. By the way, there's lots of ways to do this problem. Some people do this. They go PV over RT, because if you take cross products, PV equals nRT. They solve for the number of moles, and then they take the mass, and they divide by the number of moles to get grams per mole, and you would get the same answer either way. Okay, determine the molecular formula of the hydrocarbon. I have no idea why I put this way down here. Let me fix this quick. Let's move you up out of the way. All right. So the molecular formula of the hydrocarbon. Now, here's the deal. In A, make sure I have the pen turned on. In part A, we figured out that the empirical formula was C3H8. So let me just take a minute to figure out what that weighs. So we got 3 times 12.01 plus 8 times 1.008. And when I do that on my calculator, I get 44.1 grams per mole. That's what the empirical formula weighs. If you look at the answer for BI, we found out that the real molar mass is 44.0. And so if the empirical formula and the molecular formula are the same, that means that the molecular formula and the empirical formula are the same. This is also the molecular formula. Again, remember that the empirical formula times some constant equals the molecular formula. And so if you want to know what that constant is, so for instance, C6H6 is a molecular formula. Well, 6 and 6 has a common factor of 6. And so you can also write this like this. And so you can see that the empirical formula, which is C1H1 times 6, would give you the molecular formula. So if you want to know what that constant is, you just take the ratio of the molecular formula over the empirical formula. And in this case, it's 1. But if it was 7, then you would take this and you would have multiplied by 7. But that's a pretty easy problem. In another experiment, totally different, we get this combustion, and the heat of combustion is this, and I'm going to tell you right here because of sig figs. I don't like doing sig figs when it's in scientific notation. I'm going to take it out. This is negative 4,850 kilojoules per mole RXN. That's the new notation that came out in 2013, and this is 2003. Calculate the heat of formation. Okay, so now here's the deal. The heat of the reaction, delta H reaction, but in this case it's a combustion reaction, is the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. Now, at this case, at this point in the course, I usually haven't taught bonding yet, but all of the energy is stored in the bonds. And so the energy in carbon dioxide comes from when you take the carbon and the two oxygens and you put them together to make CO2. That's where the energy is stored, and that's what heats of formation mean. Okay, that's a little simplistic. But here's the deal. In this problem, they told you that the heat of reaction, in this case, it's a combustion reaction, so you can sub that, negative 4,850 kilojoules per mole, RXN, new notation, you won't see it online, is going up here. See this 7? So we have 7 times negative 393.5 kilojoules per mole plus 8. The 8's coming from the 8 here, because this is the heat of formation of 1 mole. Well, you made 8 times that. So then negative 285.8 kilojoules per mole RXN. I don't care if you drop that XN. Minus 1 times X, because we're trying to figure out the heat of formation of C7H16 because it wasn't given. And then minus 11 times 0. And the reason why this is an element in its most stable state, and so the heat of formation is 0 because only God can make an element. I probably said that 100 times. Okay, so then what happens is when you do this, you get negative 4,850. And notice, you can't add or subtract numbers unless all of the units are the same, and they are. And so negative 4,850 kilojoules per mole RXN minus 5040.9 kilojoules per mole RXN. Okay, I just did this and added them together, minus X, and then this is gone. And so what's going to happen is I'm going to bring the X over here, and then I'm going to bring this over here. So you're going to add X to both sides, and then you're going to add 4,850 kilojoules per mole to both sides. And when you do that, the calculator actually says X is negative 190.9 kilojoules per mole RXN. But the best answer, because this was good to no decimal places, this was good to 1. The best answer is negative 191 kilojoules per mole RXN. And that's what the scoring guidelines have. And then calculate the amount of heat release. This is a stoich problem, so very quickly I have to write this down again, otherwise it's really confusing. C7H16 liquid, that's heptane, plus 11O2 gas goes to 7CO2 gas plus 8H2O liquid. And then they told you in the problem that the heat of the combustion reaction is negative 4,850 kilojoules per mole RXN. So that's what it is when you have 1 mole here and 11 moles here, and 7 moles here, and 8 moles here. Well, now this is interesting. You don't have 1 mole. You have 0.0108 moles of C7H16. And we know that if you had 1 mole of, there's a 1 here, if you had 1 mole of C7H16, that's what there is per mole RxN. Because when this is a 1, this is an implied 1. If we were doing oxygen, it would be 11 to 1. If we were doing carbon dioxide, it would be 7 to 1. If we were doing water, it would be 8 to 1. So this cancels this, and then we know that for 1 mole RxN, we used to use reaction as written, it's negative 4850 kilojoules. So this is, remember now, stoichiometric problems are always 4 steps unless they give you moles. Well, then you don't need a step to convert grams to moles or kilojoules to moles, and so it ends up being 3 steps. And if you do that on your calculator, this has 3 sig figs and this has 3 sig figs, you should get negative 52.4 kilojoules. And that's it.